This is EE300 Linear Circuit Analysis 2, Module 2, Video 3, Network Functions and Differential Equations. First we'll have the review as usual, followed by an example, and then we'll see how we can get the differential equation, the input-output differential equation for a circuit from its network function, followed by a summary and some previews. First, the review. Previously, we've seen that there is this thing called the zero-state response network function, or just the network function. It's the ratio of the output in the S domain to the input in the S domain when you're in the zero state. Zero state meaning there's no energy in the circuit. The inputs have been zero forever, so there's no stored energy, so there's no initial condition sources to worry about. When that's that ratio of a voltage over a current, both in the S domain and a terminal pair, we call that the driving point impedance. When it's the current in the S domain over the voltage in the S domain, we call that a driving point admittance. And the admittance and the impedance are arithmetic inverses of each other. When you have an output branch variable like voltage at one terminal pair and an input branch variable like voltage or current at another terminal pair, you have a transfer function called h of s, denoted by h of s, or sometimes t of s in the book that we're using. Network functions of any flavor, whether it's an admittance, an impedance, or a transfer function, can sometimes be called a system function. That's a more abstract level where you're just looking at the signal processing usually. So we've also seen that if you have the, say, a voltage to voltage transfer function, so V of S is the output, V sub S of S is the input, and if little Vs of t, the input waveform is actually an exponential. In this case, it's got a rate S0, but we've seen that S0 could be real, so you have decaying exponentials when it's negative, you have growing exponentials when it's positive. It could be zero, which means you have a constant waveform for t greater than zero, or it could be imaginary, where you have cosine plus j sine, and we saw how you can build cosine and sine out of cosine plus j sine. So this is exponential waveforms cover a wide variety of waveforms, and there's this nice property that when the input is exponential, the forced component of the output is an exponential of the same frequency. So if the input's e to the s naught t, the output's going to have the waveform e to the s naught t. If the input has an amplitude v naught, the output is h, the network function, evaluated at the frequency of the input s naught. And that's just a number. That's a gain, really. It may turn out to be a complex valued gain when we start talking about frequency response. But the examples we've seen recently, it's just been a number. And so we also saw that as long as the input rate is slower than the output, the natural response rates, so all the poles are to the left of the input pole, then if you wait long enough, all the natural responses die away, and the waveform is just the forced response. And the forced response, if it's an exponential input, is just h of s naught, v naught, e to the s naught t. Let's work this through an example again. Here's a little different of an RC circuit. So we've got two resistors and a capacitor in series, and we're looking at the output across one of the resistors and the capacitor. So we go to say, how do we find V2 of S over Vs of S? It's just a voltage divider. So we have the R2 plus 1 over SC, the impedance of the capacitor, over the sum impedance, R1 plus R2 over plus 1 over SC, all times the input voltage in the S domain. And here I'm using V1 for the input voltage. It's hooked up to a source V sub S, but V1 is the terminal pair where the input is. So we're looking at V2 over V1 of S, both of S, and we take the expression above and multiply through by SC over SC. And then we factor out R2C from the numerator. We factor out R1 plus R2 quantity C times from the denominator. And we end up with R2 over R1 plus R2 as a scale factor times S plus 1 over R2C, the zeros at minus 1 over R2C, over S plus 1 over R1 plus R2C. The pole is at minus 1 over R1 plus R2 quantity C. Let's plug in some component values. Say R1 is the same as R2, they're both 1 k ohm. C is 250 nanofarads, that's a quarter of a microfarad. And then the input is going to be 2 e to the minus 1000 t u of t volts. So the network function with those parameters is 1/2 s plus 400 over s plus 4000 over s plus 2000. when we plug in the transform of 2e to the minus 1000t, which is 2 over s plus 1000, and then we do our partial fractions, we know that the term for the s plus 1000 term, that numerator is h of minus 1000 times v0. V0 is 2 in this case. H of minus 1000 is a half in this case. So we get 3. Yeah. And then the other term we find by just our standard cover-up method, and we get 2 over s plus 2000. So the bottom line answer is 3 e to the minus 1000t minus 2 e to the minus 2000t u of t. Minus 1000t, e to the minus 1000t is slower than e to the minus 2000t, so the forced response will outlive the natural response in this case. Now, how could we get the differential equation for that circuit from the network function? Well, in general, h of s is a ratio, it's a rational function, a ratio of polynomials, and if we write it in that form instead of factored form, we want a leading coefficient of 1 in the denominator so we can factor. So the scale factor k that sometimes is out when it's in factor form would just be the coefficient of the highest power of s in the numerator. We can assume they're equal order, numerator and denominator, because we're going to apply an input. And when we apply an input, then the product of the input times the transfer function will be a proper rational function. So we're assuming they both have order n. We're assuming the coefficient of the highest power of s in the denominator is 1. And when we do that, I mean, to find the differential equation, all we really have to do is cross multiply v2 of s times the denominator equal to v1 of s times the numerator. So when we do that, we get the denominator polynomial, which is the characteristic polynomial for the circuit, times v2 of s, and then we get the numerator polynomial times v1 of s equals the numerator polynomial times v1 of s, and then we just want to interpret every power of s as an additional derivative. We know from the Laplace transform differentiation property that when we take the Laplace transform of a derivative of something, we get s times the Laplace transform of the something minus the something at t equals 0. But we know now that we're in the 0 state, so all the t equals 0 terms are 0. So whenever we have a power of s, we can take that in the time domain to a derivative of the same power, of the same order. So the polynomial, this turns into the nth derivative of v2 of t plus a sub n minus 1, the n minus first derivative of v2 of t, down to a1 times the first derivative of v2 plus a0 times v2 equals, terms on the right-hand side, bn d sub n v sub 1 of t, etc. So we can just cross-multiply the network function times the ratio of the inputs and interpret the powers of s as derivatives. Okay, let's see how this would work. And first, let's see how horrible it can sometimes be finding the differential equation for a less than trivial circuit. And this isn't even that complicated of a circuit. So here's the same circuit we had in the example. To find the differential equation, there's one way to find the differential equation is always just to use the node method. And so then we have two unknown. V1 is sort of known because that's where we're going to hook up the source. So we'll treat that as a known node. We have two unknowns here, v2 of t and vc of t. So at the v2 of t, we take v2 minus v1, divide by r1, plus v2 minus vc, divide by r2. That's the current leaving to the left, the current leaving down. Those have to add up to 0. And then at the capacitor voltage, that's a node voltage, so the current leaving up is vc minus v2 divided by r2, and then the current leaving down is determined by the capacitor device characteristic, which is just c dvc dt. Now the trick is we got to get rid of vc of t and just get a differential equation between v2 and v1, and it's really a pain. So we can take our first equation and solve for vc of t, and here you may see how you could do this. Take vc of t over r2 to the other side, and then so you take r2 back to the other side, so you get vc of t is minus r2 over r1 v1 of t plus quantity 1 plus r2 over r1 v2 of t, and then you can differentiate that to get the dvc dt term. And so we're going to take both of those vc of t and the dvc of t, and We're going to plug them back into the second equation. We've solved those from the first equation, so we're going to plug them back into the second equation for VC of t and dVc dt, so we just get an expression in V1 and V2. So as you can see, it's kind of, this is not the biggest thing you've ever written, probably in terms of doing some algebra, but it's still a little bit gory. It's got a bunch of terms here, and there's some bookkeeping to be done so you don't screw stuff up. So the first thing we notice is when we put these all together, in the middle term in brackets and the right-hand term minus V2 of t, there's a V2 of t minus V2 of t that goes away. Okay, that's nice. So then we take the V1 of t terms to the right-hand side and leave the V2 of t terms on the left-hand side. And we do this, we notice we've got an extra R2 in the numerator here. So we can just get rid of all those. And now it's just a matter of multiplying through by R1 on both sides and doing the algebra. So we multiply through by R1, and then we factor out R1 plus R2C from the left-hand side. We factor out R2C from the right-hand side, and we get back the differential equation dV2 dt plus 1 over quantity R1 plus R2C V2 of t equals fraction R2 over R1 plus R2 times all of dV1 of t dt plus 1 over R2C times V1 of t. You look at that, you say, hey, that looks like the transfer function we had. We had we had R2 over R1 plus R2 times S ds plus 1 over R2C V1 of S all over S plus 1 over R1 plus R2C V2 of S. So you see this is where our transfer function comes from, and here's how we would do it now, just using the transfer function. You take the transfer function we found earlier, which again is R2 over R1 plus R2 times S plus 1 over R2C over S plus 1 over R1 plus R2 times C. We're going to cross multiply those, so we get S V2 of S plus 1 over R2, R1 plus R2 times C, V2 of S. And then we have our equals R2 over R1 plus R2 times S V1 of S plus 1 over R2C, V1 of S. And then we're just going to interpret S's as d by dt's. So there we are, dv2 dt plus 1 over R1 plus R2C, V2 of t equals R2 over R1 plus R2, quantity dv1 of t dt plus 1 over R2C times V1 of t. 3 steps. It took 3 steps to get there from the circuit, whereas the other case, we had all this algebra, we had canceling, we had bookkeeping. So this seems to be a preferable method, and it works whether the input and output are in terms of a device element. I mean, up until now, we've only looked at differential equations in terms of device parameters, capacitor voltages, inductor currents, and the like. Now we can find differential equations in output variables, even if they're not directly a device variable. So to summarize, we already know we can find the network function using impedance techniques and resistive circuit techniques, voltage divider, current divider, node, mesh, etc. And now we can find the input-output differential equation from the network function just by cross-multiplying and interpreting S as d by dt. So what's next is to figure out what poles and zeros mean. And that's really going to be the completion of our story about what do network functions mean and what do they do. We're going to be using them for the rest of the semester. But the next step after that is figuring out how to design circuits to implement particular network functions. So this has been EE300, Linear Circuit Analysis 2, Module 2, Video 3, Network Functions and Differential Equations.